Okay, let's go back to here. And before we enter next topic, which would be the introduction to intrusion detection, I would like to revisit some other concept I would like to emphasize. Okay, which is right here in our very early slide, which is T09, problematic data. Okay, so if you have your collab, okay, try open it. Okay, here is it. Okay, we have explained some content in this slide, problematic data. We mainly focus on how to do downsampling, how to do upsampling to deal with unbalanced data, okay, or imbalanced data. Okay, so that's it. Okay, so we skip this one. I would like to go to here. Okay, some example of overfit or underfit. Okay, when we talk about overfit or underfit, okay, of a model, we usually means if your model is overfitted, which means your model is too complex. Your model has too many weights, too many different mechanisms, so that your capacity of your model is very large. So in that case, your model can easily remember the relationship between your data, input data, and output target Y. It does not. It just simply remember the answer because it has many weights, many neurons, and they can use different neurons to remember specific answer of a specific input. Okay, so usually when we say underfit, when we say overfit, it is. Okay, so on the contrary, underfit means your neural network has only very few neurons or layers, so the capacity of your neural network is very small, so that your model cannot correctly present the relationship between your input and output. Okay, so that is the definition in my mind. Okay, so of course the data we use as the demonstration right here is not neural network. Okay, it's just a very simple nonlinear regression. Okay, so we have you can see that. Okay, the true function, which means the actual function. Okay, and we have several different data set. Okay, training data set and testing data set. Usually, okay, again, I would like to make an emphasis right here. Usually, when we do machine learning or neural network, no matter what it is, okay, we have an assumption, which is your distribution of your training data set and your testing data set should be the same, or at least should be similar. Okay, and I think that is a very very nice example. You can see that the true function is the actual distribution, no matter what is the relation between the x-axis and y-axis. Okay, the relationship is the blue line. Okay, so the sampled training data, okay, which is quite close to the true function, and the sample testing data is quite close to the true function, so that we can learn this true function by using the black dot, which is the training data set. Okay, so we believe no matter what kind of regression model we use or the neural network model we use, they can try to represent this blue point by using the data. So try to represent the blue line by using the black dots. So when we do testing, which is the red dots, comes to our model can do such kind of prediction so that we can, so every time the new test data point, I think the red one, it's right here. Okay, for example, that is X and that is Y, that is our target. Okay, so every time it's right here, we can successfully predict its target. Okay, every time the new data point, testing data point right here, okay, I can predict its target. Okay, because I have those black data point. But sometimes, as I think we talked about it in last week, sometimes when you collect those data point, okay, one problem is your training data point, which is the black dot, does not quite fit to the true function. That means you have bias. Okay, you have bias. Your data point maybe, okay, I say maybe, okay, one of the situation problem might be like this. If your neural network is not perform quite good, you have to think about it. Okay, maybe the data set you collect from I don't know, from somewhere, maybe you only collect the data right here. So you think, okay, this data set might look quite easy because it looks like linear. So you may create a wrong regression line such like this. But we have a doubt right here, right? You cannot correctly represent the data at the right hand side because simply just a very simple line to represent the data at the left hand side. But this is the problem of data collection. You do not collect the entire distribution, which is the blue line. You do not collect enough samples, enough data point through the entire distribution. So your model may not correctly model the data at the right hand side. Okay, so basically you have to, when you do such kind of training and testing, okay, make sure your tested data point has the same range as your training data point. Right here, okay, the data point, okay, of course we have only one feature, which is x1. Okay, if your sample data is between 0 and 0.4 and your testing data is far way beyond 0.4, that means your model is unlikely to represent the data at the right hand side, which is beyond larger than 0.4. So your model might fail. Okay, so make sure you indeed do such kind of check. Okay, when you perform your model. Okay, that is one of the things you have to take care of by yourself. Okay, model will not help you to do such kind of check. You have to do such kind of check by yourself. Okay. The other I think the most of the model may fail is due to the following reason. Okay, you have a very nice sample, which is all those black data points. Okay, you model all those data points, black data point. Okay, however, when you do testing, okay, your testing looks like this. That means when you collect your testing data, your data does not fit to your true function. How it happens? For example, if we collect the training data, okay, for example, a black data point, for example, you collect the children's weight and height from an elementary school. So you create a model, you can perfectly describe the training data of height and weight of many children in elementary school. However, when you do such kind of testing, you use students in university. However, you cannot guarantee the distribution of data in an elementary school and the data in university is the same, unless you can prove it first. So sometimes, for example, if you would like to study some data in Taiwan, but you use the model created from some other region, for example, from the United States, maybe the distribution of the data in Taiwan and the United States is the same, but most of the time they are not. So some project they failed because the model is correct. They can perfectly fit the training data, but the testing data is you do some irrelevant data. Try to use the irrelevant model to predict the irrelevant data, testing data. So the data should not be the same. The performance of the model will be very, very, very bad. Okay, so that is one of the reason. Okay, but the other reason is that something like this. I think we have talked about before. You use a wrong model. For example, the true function is the blue line, and your observation is the black dot. However, it looks like a nonlinear relationship between your x and y, right? But you use a linear model, right? So here is the testing data. Okay, if you use your test data right here, your prediction would be very, very worse. Okay. But however, this kind of situation only occurs when you use a very basic model. If you use a more complex model like neural network, you have many different layers, you have many different neurons, you choose some very advanced activation function to simulate their non-linear relationship. Most likely, okay, your model will try to fit such kind of non-linear data. So basically, if you use neural network, such kind of a situation will not exist, okay, unless you use a very simple polynomial or a linear model. Okay, so but even if you use even if you use neural network, okay, let's take a look at these overfitting problems. Okay, that is one of the way. Okay, the true function is the blue line, and your observation, your training data is the black dot. But you can see that your model is too complex. So you can see that your model try to remember the result of your black dot, okay? Because the capacity of your model, as we can see that right here. Of course, this example is a polynomial example. Okay, it may, because it's 25, so it may looks like something like something like that. This is quite complex. You have too many weights. For example, we have 26 weights right here, right? Sorry, I should write it in this way. Okay. Right. Something like that. Okay, so we have too many weights. But what is the reason why if we have too many weights, we can remember the data? Okay, I would like to draw a figure right here, so make sure you understand. Okay, for example, okay, if we have only very few input, for example x x1, x2, and we have output y right here. Okay. If, for example, if we have n data, okay, so let's make it very small. So if we have only 5 data, like this, if we have only 5 data, okay, so we can say that if we have many hidden neurons right here, let's make it a very simple neural network structure, but we have too many neurons right here. Okay, so when the very first data comes here, okay, we can put it for example right here. Okay, yes, S1, S2, and Y right here, right? So if the data right here, that is, let's just take an example now. That is 2 and 5, and the result is, for example, 8. That is the very first data you will. So when 2 and 5 comes here, okay, and we say this is a neural network, so we connect the relationship right here, right? And well, we have another weight, right? Such as this one. We have another weight such as this one. If your neural network is very complex, which means you have many weights, your capacity is very high. Okay, so basically, you can use a neuron right here. Here's H1. This specific neuron H1, it's only focused on the very first data set. So the weight right here is 1. The weight right here is 1. Okay, and for some reason, okay, so the other weight, okay, we can say that this neuron only specific used for the very first data set. So it can output, for example, it can output 8 for some reason. Okay, of course you can tweak this weight, which is okay, this weight, which is okay. So that means this neuron H1 maybe, okay, it does not activate for all the other data set. It is possible if you have a very large neural network, you have very large weight. Okay, and even though I can even draw a very very strange neural network. Okay, like this. Okay, we use this one. This we have x1, we have x2, we have this specific neuron h1, h2, and 2, hn. Each neuron only receive each neuron has for example has a convolution layer. Okay, the first convolution layer right here. The first convolution is like that. It has only two. This kernel has only 2 values. The first one convolution is 2 and 5. The second convolution is 3 and 7, and so on and so forth. The last convolution is 7 and 2. We can create a very specific convolution layer, which means, of course, every data, okay, has to every convolution. But only the first convolution kernel right here is only active to your first data set, first data point. So it will be activated right here. So H1 will output 8, for example. The rest of the, of course, H1 will be connected to some other convolution layer. But you know, this value 3 and 7, the weight will maybe, okay, it does not active to 5. It only active to your second data point. So every time when you input your second data point 3 and 7, the first neuron, the first convolution kernel will not activate such kind of data. Only this one will activate its data. So after that, a specific neuron H2 will output, for example, 1, 1 right here. So let's, of course, it is a very strange example. It's a very extreme situation that we have a very specific structure only activate by very specific input, and it will output the exact value of its target value. Okay, we can create such kind of a neural network. So such kind of a neural network, I use the word remember or memorize. They can memorize the input and output if you have a very large and very specific neural network. It can do so. So such kind of neural network only memorize the data. Okay? If you input a new testing data, for example, right here, if you have a new testing data, it is 1 and 2. And you will figure out that all those convolution structure right here would not activate such kind of input data, so that it may not output the correct Y. Maybe the answer is 3. So that kind of neural net is extremely overfitted because you have too many weights, and the capacity of this neural net is very large enough to that the neuron to remember certain input data and its corresponding output Y. So in this case, we don't want to do so. So we introduced several different technique before. For example, we can use dropout, so that some of the neuron will not receive specific data. Okay, those data are randomly dropped when we do such kind of training. So each neuron right here at the right hand side, they will try to receive information from different sources, not a specific sources. So that's the reason why dropout works. Okay, and then next one, you have to not that, okay, I would say that not that many layers and neurons, which means every time when you create your neural network, don't make it too complex. Complex neural network only fit to very large data set. If you have only few hundred or few thousands data points, you don't have to create a very complex neural network, because that kind of neural network would tend to memorize the relationship between your X and Y. Okay, so that is my suggestion right here. So of course, we have another approach to deal with such kind of overfit or underfitting. It's called validation data set. Okay, so okay, I'd like to show you some something about validation. Usually, okay, if you collect some data, and again, I have to mention it, you have to make sure your data collection is really from the entire of your data distribution. Okay, so if I use these things, that means when you collect your data, make sure all your data point among the entire your true function will be sampled. Okay, so that you can create very nice data. So most likely we have training data set, right? And of course you have to set your testing data set, okay? So that you can, every time you create your model, you can test how good your model is, okay? However, usually we would like to that is testing. My recommendation is after you collect your data, okay, you partition your data into 3 different data sets. One for training, the other for testing, and the other for validation. And you have to make sure all those 3 data sets has the same distribution. Okay, have the same distribution. That's the same division. Okay, when you do partial differentiation, you use the data set in your training. And of course, as we mentioned in the previous hour, you can partition your data into some mini batch, okay? And you train your data using this mini batch, okay? That is training data, okay? At the end of your training, okay, you use your data set, tested data set, to calculate how good your model currently is. Of course, you don't train your tested data in when you do training. Okay, so test data only use once when at the end of your training, and that is your result. That is your test result. Okay, so how about the third data set, which is validation? Okay, so that is every time when you train your data, your model, okay, you do the partial differentiation, you update your MSE or cross entropy, okay? Every time when you train your data, okay, when you do training, okay, you use your validation data set to do validation, okay? So, for example, if you train your data 100 times, you have 100 times of partial differentiation to improve your data, okay? So every time you finish your partial differentiation, you test your current model by using your validation dataset. Of course, it gives you the accuracy of your current model. It gives you your loss value. For example, you use MSE, you have the current MSE value, okay? So you have to observe something like this. So that is the error value. Okay, this is the error value. Okay, you have to test it. Also, at the very first beginning, okay, your initial learning rate might be large. Okay, so you have a right direction to your lowest loss function value, right? So your loss error may decrease very nicely and quickly. And after several field training epoch, okay, and you can see that, okay, I think I use this one would be better, right? Okay, that doesn't matter. Okay, it's almost the same. Okay, when you do the validation, you can observe the current loss. Okay, if the current loss value, okay, like this, right? Loss of validation, and we have different at 1 to 100, and usually the loss function may look like this. Initially, it decreased and will stay somewhere, which means your model is quite stable. When you try to do further training, okay, those data points would not further decrease your loss value. So you can use the validation function, validation dataset to test if your loss value would stay somewhere stable value. Okay, if you keep training your data many times, which means you have several different rounds, those n data, you use them multiple times, 100 times, 1000 times. Okay, in that cases, okay, your training accuracy will be very, very high. That is because your model now will try to memorize the data right here and its corresponding target value. That means your model will gradually become overfitted. Okay, so in this case, since your validation data has never been trained, so you can see that you're you can see that your validation data's loss will become higher and higher because your model, currently your neural network model, will currently has been trained too many times by using your training data. So your neural network will try to memorize the answer between your x and y. So your model lost generality. 中文应该就翻译说你的模型失去了一般性，它越来越专一化了，因为你 training data 太多次了。So we can use validation dataset to verify if your model become more and more specific to the training dataset. Okay, so maybe you should stop your training right here. So we call it early stop. Okay, you can find some settings in Keras or TensorFlow. Okay, they teach you how to stop your model early, so that your model will keep the still general to all the datasets. Okay, so after you do such kind of early stop, okay, you don't do training again, then you test your data, and that is your result. Okay, you have your training, but you don't know how many times you need to train. That's okay. You can use your validation dataset to see if such kind of situation occurs. Okay, of course you can. There's a parameter right here for your validation. Okay, if your loss of validation, okay, is quite stable, okay, and it suddenly recurs, okay, you can define what it means suddenly. Okay, there's a threshold right there. If it suddenly decreases, then you should stop your model. Your model becomes too overfitted. Okay, so you can use the weight right here. So that will quite nice to your training data and not overfitted. So after you do such kind, you do your training, you can you do your test, then the result will be good. So here is the result right here. Here's an example right here. So the blue dot is the number of times you do training. Okay, it says degree. That means because the example is polynomial, but we can use the exactly same thing right here. Every time when you do the training, okay, if you don't want your model to be overfitted, okay, you can set different number of layers and neurons, and you can set different runs of your epoch to do training. Okay, you can tweak those hyperparameters. Okay, so the result will be like the same. Your training error will be less and less and less. That is because your model is overfitted. So sometimes you need another dataset to help you. Okay, you should not do training anymore. You should stop right here. That is good enough. Okay, so that is okay. I think that is enough. And the right here is the regularization, which we have talked before. Reg and the lasso regression. Okay, it's quite simple. It's just simply like this. When you design your loss function, okay, remember, okay, add something like here. The theta is all the weight. We have to minimize this weight so that some of the weight will become 0. That means some of the neuron will not activated. That means some of the neuron will die. We use this word dies, so that maybe you have too many neurons, too many weights to describe a problem, right? But after you apply this, some of the neuron dies. If the neuron dies, that means your capacity, the capacity of your model, which is the number of weights you want to use, decrease. That means it helps your model to only keep some of the neurons, not all of them, so that your model may prevent overfitting. Okay, so remember to use these things. Of course, there's a weight over here, so you can try to balance between how many neurons you would like to make them die, or you would like to minimize your loss. Okay, so basically try to use them. Lasso, okay, is only power of 1. Okay, rigid, it is power of 2. Okay, make sure you understand it. Okay, so I think that is. I think we can stop right here. Okay, so I think that is all of the neural network things, all the learning things I'd like to talk about. So in the next hour, we will talk about intrusion detection. Okay, let's take it's okay. Let's take a break for 18 minutes. Okay, please come back 10 after 11. Okay, 10 after 11. So next hour we'll talk about intrusion detection and anomaly detection and misuse different kind of detection systems. Okay, let's stop right here. Take a 20-minute break. Okay.